All right, so we're going to finish up chapter 5. So this is section 5.5. It's on logs. So remember in the last section we talked a little bit about logs, we talked about properties, but what we didn't really get into is graphing them. Okay, so we're going to look at doing some sketches. We're going to look at the transformations, which is exactly the same as the transformations we always do. And then we're going to finish up with an application of logs using what's called the Richter scale. Okay, if you haven't heard of it, it's just used to measure like the intensity of an earthquake. All right, so first thing we're going to look at is what's called the change of base formula. Okay, we've kind of worked around not knowing this using different properties, but this property is going to kind of lessen the amount of work we have to do to solve some equations. All right, so when we have something that is exponential, what does that mean you have? In order for an equation to be exponential, you have to have basically two things. Anybody remember one of the two? Yep.
An exponent?
Yep. Where does the exponent, what kind of exponent?
A variable?
Yes. You have to have a variable in the exponent. And one other thing. Anybody remember the other thing we have to have about the base? Yep.
Does that have to be a real number?
There is a condition on it, but it can't just be any real number. Yeah?
Positive, real, a real integer.
It has to be positive. It doesn't have to be an integer, though. But even though it can be positive, there is one number it can't be. Yeah?
Like more than one?
Well, if it's more than one, that would be exponential growth. Yeah?
Can't be 0.
Well, it has to be positive, so we got that. But there's one number that it can't be that's positive. Yeah?
Anything above 0 excluding 1?
Excluding 1, yes. So the base has to be anything above 0, but not 1. And it has to have a variable for an exponent. So let's say we had something like 8 equals 2 to the x. 2 to what power would give you 8? Yeah? 3. Now, how come that one was pretty easy to solve? Because in general, solving when you have a variable as the exponent, it might not be that easy. But what made that one easy? Yep.
Everything's positive.
Um,
That 2 goes into 8.
well, I could give you something where everything's positive, and that's going to become a lot harder.
Because 2's a factor, right?
So 2, well, yeah, 8's a power of 2. Yeah, so 8, you can raise 2 to a power and get 8 without using any decimals. Yeah.
It's a perfect cube.
Yeah, so because it's 2 cubed gives 2 cubed gives you 8. So that's the key that made that one easy. This one's not as easy because 3 to a power gives you 5. Well, 3 to the first power is 1. 3 to the second power gives you 9. So it's somewhere between 1 and 9. Okay. All right. So now let's look at this one. What makes that one hard to solve is the fact we have the x in the exponent. We had a rule that allows us to put the x in front, but only if you have what function in the equation. You can't just move variables in front unless you have this on both sides. Yep.
Log.
A log. Okay, so if we take the log of each side, we have that. And now we can take the x on the right side and put it in front. And what would be my last step to get x by itself?
Divide by log 3.
Yeah, divide by log 3. So divide each side by log 3. That's gone. And we get x equals log 5 over log 3. Now, what I want to look at is going from that box directly from what we started with. Actually, no, let's take what we started with first and rewrite it. how could you rewrite that top equation in log form? Yep.
Log base 3, 5.
Log base 3 of 5.
Yeah,
Yep.
that equals x.
Equals x. Perfect. So the only reason we didn't write it that way to start with is because the calculator can't do log base 3 by pressing a single button. Does anybody remember the two bases it can do? Yeah?
10 and
Right, it can do 10 and it can do e. So look at what we had here, okay, by changing to log form, and look at what we got here. We know that this and that must be the same thing, because they're both equal to x. It was just a different way to get x. This way, we'll call that box 1, we can type in on the calculator because we have a button for base. Well, actually, you tell me, what base is that when I don't write the base on a log? Yep, base 10. That I can type in on the calculator because it's 2 base 10 logs divided. This I can type in, but we haven't learned how to type it in yet. But now, if you look at from box 1 to box 2, I want you to see if you could try this one, log base 6 of 13, without changing it back to exponential form and then doing all that stuff we wrote in black. I want to see if we could just figure out a way to get a formula for x using the pattern we see right there. Anybody think they know what would go on this on the left side? If you went through all the steps in black all over again. Yep.
Log 13 divided by log 6.
Yes. And can you explain how you got that?
I believe it's for the base of for the log 6. That's going to be the divider of the whole equation, and then
So
log
you
13,
divide by the log of the base, yep.
and then you multiply 13, or you have log 13 on top.
And what do you call the 13 again? What's that called?
Not sure.
Anybody remember what the 13 is called? Yeah?
Your
The argument. And that's basically the formula. If you take the log of the argument and you divide by the log of the base, that's how you type something in that's not base 10 or base e, without having to go through all those steps in black. Okay, we can just go right from that step to that step. And that's called the change of base formula. You've changed your logarithm, so it's no longer base 6, but now it's a base 10. Right? And there's actually two ways that you can do that. You can either do it with base 10, or you can do it with base, what's the base on ln, even though it's not written? Yep. E. Yep. You can do it either way. Okay, and that's called the change of base formula. And let me show you that it would work either way. Right, if you take, let's take log of 5 and divide by log of 3. Okay, you get that as an answer. If you take ln of 5 and divide it by ln of 3, you get that as an answer. Okay, so it comes out exactly the same, no matter which version you use. Whichever type of log you use, stick with that log for the whole problem. Don't mix an ln and a base 10 log. Okay? Either use all base 10 or use all base e. Okay? Just like the formula shows. Okay. Any question on that formula? Yeah.
Is there any reason like why this works and why log base or log 10 x over log 10 b equals log or natural logarithm of x over natural logarithm of b?
So why that formula works? Well, the best thing I can kind of show you why it works is using doing it this alternate way, right? We know that this works from properties of logs. You can take the exponent and put it in front, and we learned why you can do that the week before. So if we use the properties we already know, we get an expression for x. And if we use the property of changing an exponential to a log, we get a different expression for x. But since they're both equal to x, that means circle 1 and circle 2 must be equal to each other. So kind of thinking of it like the transitive property, this equals x, that equals x, so they must equal each other, and that's basically what that law is saying. Yeah. All right, so now let's graph that one on the calculator, and because it's not a base 10 or a base e, we have to rewrite it to type it in. How can I rewrite that logarithm so that I can type it in on the calculator using the change of base formula? Yeah. Sure, we could do ln x over ln 3. You could have also done log x over log 3. It would come out exactly the same. Yep. All right, so now let's graph that. Make sure when you do it that you close your parenthesis because it's going to open one when you press ln. So ln, at least on mine, it opens it. As long as you close it, you do not need parentheses around the whole numerator and the whole denominator. You can type it in just like this. All right, and let's do zoom 6. Now remember, the calculator doesn't always do a perfect job graphing it, so we can look at that, but we might need to be a little bit intelligent when we describe the domain and range. Okay, let's start with the domain. What is the domain here? Yep.
I was going to say, can you put ln and log?
Oh, did I mix them? I did exactly what I said not to. Thank you. It's not going to make a huge difference with how the picture looks, but it's a little different. Yeah. All right, so now let's look at that one. What I did by making a mistake there, it wouldn't have changed, actually it wouldn't have changed the domain or the range, but the picture would have been wrong. All right, so we'll start with domain. What's the domain here? Yeah.
X is greater, or so it would be open parentheses 0
Okay.
is, I'm forgetting words here, less than X. Or no, it's greater than 0, but not equal to 1. I'm forgetting words right now.
Okay, so I like the parenthesis. Let's start with that. That's a good start. So parenthesis. Yep. 0. Why don't we include 0? What's going on over here? And the calculator's not doing a great job of showing it. Yep.
Well, it's not actually reaching 0.
Why? What's happening in the graph right here?
It converges to infinity as x approaches 0.
As x approaches 0, the graph is approaching negative infinity, which means you have a something in this graph. Yep.
Vertical asymptote.
There is. There's a vertical asymptote right there. All right. So if we were to sketch that and really draw it by hand, it should look more like that. And you've got a vertical asymptote right there. Yep. So the domain is going down to 0. And how high is it going? Up to, yep, up to infinity. Yep. That's the domain of every log function, unless you transform it, which we'll talk about in the next section. Like if you, or next slide. If you shift it right 1, then the domain would be 1 to infinity. All right. All right. How about range? Again, looking at that picture isn't a great representation of it. I would think more about that picture right there. What's my range? Yeah.
Negative infinity to infinity.
Yeah, negative infinity to infinity. All logarithms pretty much go down forever and up forever. You can't change that. Okay, so we got domain, we got range, and there's our graph right there. Okay, any questions on that? Okay, so even though it looks like that graph has a start point, it doesn't. Okay? Square root functions have a start point, but that is not a square root, that is a log. Okay, all right. Okay, so transformations. Again, I'll write them down. This will be our last time we go through them with in the algebra part of this class. The next time we see this type of transformation is when we talk about trig functions, like sine and cosine. All right, let's start with A. Hopefully by now we know these pretty good. What type of transformation is A? Adding or subtracting, could be either one, inside. Yep,
Horizontal shift.
that's your horizontal shift. Positive would move it to the left, and then negative would move it
To the right.
to the right. Yep, it's backwards. Okay, how about B? Yep, James.
Horizontal stretch.
Horizontal stretch. And again, that is also backwards. So if you put in a number like log 3x, 3 is a big number, it actually compresses it, makes it stretch by 1/3. If you did something like log 1/2 x, 1/2 is a small number, but it actually makes it bigger. Log 1/2 x would stretch it horizontally by 2. All right, C and D are not backwards. Okay, what does C do? Yep,
Vertical stretch.
that's your vertical stretch. So if you graph like 5 log x, that's a vertical stretch by a factor of 5. And how about D? Yep,
Vertical shift.
vertical shift. And again, that one is not backwards either. So log x, something like this. That's a vertical shift up 3. If b is negative, that would cause my graph to do what? Yeah.
Flip over the x-axis.
So if b is negative, that would be a horizontal reflection. And if you reflect horizontally, that would be over the y. Yeah. If c is negative, that is a vertical reflection, which would reflect over the x. Yeah. Okay, so all the transformations that we already know are exactly the same for logs. All right, so let's try one. Now, the first thing is you always have to compare logs with the same base. You're not going to compare a log base 3 to a log base 6. That wouldn't work. Just like when you're doing roots. You're going to compare a cube root to a cube root, not a cube root to a fourth root. Okay, so here's the original, log base 3 of x. And here's the new one, log base 3 negative x. Right, so I just want to know what the transformation is. And then I want to know the domain, the range, and the new vertical asymptotes after the transformation. Okay, let's start with how many transformations there are. Yep,
Just one.
just one. Okay, so let's make a list. Okay, what's my one and only transformation in this one? Oh, Nick.
Horizontal reflection.
Yeah. Okay, the stuff inside the parentheses is always your horizontals, and it's a reflection because it's a negative. Horizontal. So that describes the transformation. Now, if you remember the domain and range of the one we just did, this one is a reflection. Okay, so it's going to be, instead of going to the right, it's going to go to the left. So let's start with the domain. What do you think the domain would be if you reflect a log function over the y-axis? Yeah.
0,
Negative infinity to 0. Yep. Make sure you always put the low value, then the high value. So that would be your new domain. How about the range? What would happen to the range if you reflect a log function horizontally? So it's going to look something kind of like that. Keeps going. Yeah.
Negative to positive infinity, it stays the same.
Yeah. So the range, that can't be changed no matter what you do. So domain, range, and the vertical asymptote. Whenever I look for an asymptote, I'm always going to ask for an equation. So what would be the equation of my vertical asymptote? Yeah.
X equals 0.
Right. Because you reflected over the asymptote doesn't move. So it stayed the same. All right. Any question on how you would sketch that on the calculator if you needed to double check anything? Or how we found domain, range, and the asymptote? Okay. Here's another one. Let me just add some stuff to it. Let's make it. Okay. So 4 log, in parentheses, 3 minus x minus 5. Okay, so first thing, does that setup look like the template that I gave you? What do you think? Yeah, cool.
If you were to switch X and zeros and 1,
Right. What's inside the parentheses, that's not in the right order. Okay? It should always be the number with x first, and then the number that's by itself for the horizontal shift last. Okay? So can you tell me, Clover, how you would rewrite that?
that would be negative X plus 3.
Yeah, so we'll keep everything else the same. And this time they're not asking for domain, range, or asymptote. We could figure maybe we'll do one of those, but let's just start with the transformations. All right. What's the first transformation that's going to happen here? Well, Dex, can you tell me my first one?
Looping a horizontal shift to the right.
Shift, and we have a +3, so that's going to be to the
To the right 3 units.
to
To the left.
To the left. Remember, the horizontal is backwards. So shift left 3. Lizzie, what's the second thing that's going to happen?
Is it the 4?
The 4? No, not the 4 yet.
Oh, it's like a reflection, right?
Yep. What kind of reflection?
Vertical or horizontal?
Horizontal, right? Because the negative is inside the parentheses. That's a horizontal reflection. How about next thing that's going to happen? Yeah.
It's going to be a vertical stretch. 4.
Yeah. So vertical stretch by factor of 4, and then the last thing, James, what's the last thing that happens?
Vertical shift down 5.
Shift down 5. All right. Now let's do the vertical asymptote. Let's find the new vertical asymptote. Which one of those? Well, yeah. There's 4 transformations there. Not all of them are going to affect a vertical line. Which transformations would affect a vertical line if you did them to it? Yeah?
1 and 3.
I agree, one would. But if you remember, a vertical line goes up and down. How long is a vertical line? Infinite. So if you take something that's infinitely long and you stretch it 4 times as much, how long is it now?
Same.
It's the same. So yeah, stretching vertically will not affect a vertical line. So one will. Anything else that will affect the vertical line? Yeah?
2 and 4.
Well, we already said one does.
So 2 and 4.
So,
We're changing direction entirely.
okay. So if you have a vertical line, how long is it?
Indefinitely.
Right, it goes up and down forever. If you shift it down 5 units, where is it now? Compared to where it was before.
Yeah, 5 years. Probably not.
Would you notice that?
Not really,
No,
no.
because it goes up and down forever. So shifting something up and down that goes up and down forever, you'd never notice it. Yeah?
It's going to be 1 and 2.
1 and 2. These are the only 2 things that would affect your vertical asymptote. 3 and 4 have nothing to do with it. 3 and 4 would affect like the range if we wanted to look at that, but they wouldn't affect the vertical asymptote. All right. So now let's do these 2 things to the vertical asymptote and think where it would end up. Where is the vertical asymptote if we don't do anything to it at all? What would be the original equation? Whalen? Sure. Anyone help him out? What's the equation of the vertical asymptote for a log function? Yeah.
X equals 0.
It's at x equals 0. So let's start there. If we shift that left 3, where would it end up? Yep.
X equals -3.
It would be at x equals -3. So now it's over here. And if you did a horizontal reflection, where would that dotted line end up? Yep.
X equals +3.
X equals +3. Yep. So that's how you could figure out your new vertical asymptote. Just think of where the original is, and then do the first 2 transformations. How about the domain? That's your new asymptote that I just checked off. And remember, a log function is only going to curve one way. So is it going to be everything greater than 3? Or is the domain everything less than 3? Yeah?
Everything less than 3?
Right, because a normal log function would go to the right. But you did a horizontal reflection, so it's going to make it curve left, like that. So the domain in this problem would be everything less than 3. Which you could write as an inequality, or you could write as an interval. Doesn't matter. Range, all real numbers. Okay, no matter what you do to the range, never changes. All right, so that was a little more complicated, but any questions on that one? Okay. All right, so now, let's do a sketch. So when we are sketching a log function, generally what we want to do is make sure you find the vertical asymptote. Because once you have that, that gives you the line that it's going to bend away from. It's either going to do something like this or do something like that. Okay, so find the vertical asymptote so you know which way it's going to bend away from. And then, if we can try to find the x and the y-intercept. It's not as important as finding the asymptote. Which intercept will a log function always have, no matter what kind of transformation you do to it? Yeah?
X-intercept.
It'll always have an x-intercept. Why will you always have an x-intercept?
Because the range is always negative to positive infinite, so it has to cross the x-axis. at some
Perfect.
point.
Yep. The range is all real numbers, and it is a continuous function. So you're always going to cross the x-axis. But you might not cross the y-axis. If your asymptote is the y-axis, you'll never reach it. Yep. All right, so we kind of thought about the vertical asymptote just step by step last time. I said, think about where it would start, then do transformation 1 and transformation 2. Okay, these are the only two things that affect the vertical asymptote. That's the A and the B. Okay, that's the argument. So if you set the argument equal to 0 and solve it, that's another way to think about how you can find the vertical asymptote. It's exactly what we did in the last problem. This is a different way to think about it. Just a reminder, if you don't remember, x-intercept is when y is 0, y-intercept is when x is 0. If you need more points, as always, we just use the calculator, use the table, and you can get points that way. But remember, we talked about logs. You cannot plug in a negative, because that would get into imaginaries, and we don't want that. If you accidentally plug something in that goes the wrong way on your graph, your table's just going to say error. That's all it's going to do. All right, so let's try an example of sketching a log. So it says to sketch log base 2 of 3x plus 5. Okay, first of all, let's do the asymptote. What kind of asymptote does a log function have? Horizontal or vertical? Yeah. Yeah, vertical. So let's find that. What did I just write down in the directions? To find the vertical asymptote, do this. Yeah.
Set the function equal to 0.
Set the, can you be more specific?
Set the log equal to 0.
What about the log? Not the whole log. I don't think, it didn't say set the log equal to 0, did it? I hope not. Yeah?
Set the argument equal to 0.
Set the argument of the log equal to 0. Just the argument, because that's the only part that's going to affect the asymptote. So that'd be 3x plus 5 equals 0. Now think about what's going to happen from transformation point of view. It's going to move it left 5 units, and then it's going to horizontally compress it by 1/3. Right? So if you start at 0 and you go left 5 units, that puts you at -5. And then if you compress that by 1/3, it's going to move you closer to the origin. Right? So let's solve that. So the first step, we get the -5. That moves the asymptote left 5 units. And now the 3 is going to compress the distance by 1/3. So that's why when you solve it, you divide each side by 3. So that's your new vertical asymptote. It's -5/3. All right. Let's also do the Let's do the y-intercept next. What do I plug in to find the y-intercept? Yeah. We're going to plug in for x, and what number are we going to plug in? Yeah?
0.
Yeah. So the x-intercept is when y is 0. The y-intercept is when you plug in 0 for x. Okay, so let's plug in 0 for x. We get y equals log base 2. And when you fill in 0, it's going to be 3 times 0 is 0. 0 plus 5 is 5. Okay, so I get log base 2 of 5. That's my y-intercept. Because that's not base 10 or e, I do need the change of base formula. So it's going to cross the y-axis at about 2.3. So we got the intercept. I'm not worried about the x-intercept. That's fine. We don't need to find that. Maybe we should practice. Okay, x-intercept is when you plug in what number for what letter this time. Yeah.
0 for y.
0 for y. Actually, it's not 5. What was it? 3x plus 5. Okay. Now to solve that, what could I, what format could I change that equation to? Voices. Remember from last week, what can we change that to? Think about what it is now. Yeah?
It would be log base 2 3x plus wait.
Looking for a way to get rid of the log. Yeah? Change it to exponential. Yeah, what would that be in exponential form?
3x plus 5 equals 2 to 0.
Yep. 3x plus 5 equals 2 to the 0. Anything to the 0 power gives me 1. And now just solve and you get x by itself. So 3x equals negative 4. And that is my x-intercept. Negative 4/3. All right, so we've got the asymptote, we've got the x and y intercept. Range, well, that's a quick one. What's my range going to be for the log function? Yeah?
Negatives, positive, infinite.
Yeah. It's always going to go up and down forever. And once you get the vertical asymptote, then the domain is pretty straightforward. It's either everything smaller than it or everything bigger than it. So I'm going to do x, vertical asymptote was negative 5/3. And which way is this graph going to curve? To the right or to the left? Yep.
To the right.
Yeah, it's going to curve to the right. Standard log function always curves to the right. The only way you can make it curve left is if you put a negative in the b spot, but that doesn't happen. So does that mean my domain is everything bigger than negative 5/3 or smaller? Which way would make it go to the right? Yeah, bigger. So other than making the sketch, that's everything they wanted. Now let's make the sketch. Okay, let's use that. All right, so So I got my x-intercept, that's about negative 1.3. Negative 1.3. I've got my y-intercept, that's 2.3. Right there. I've got my vertical asymptote, negative 5/3. That's negative 1 2/3. So about negative 1.6 repeating. So let's put that in. Oh, right there. So I can see it's how the curve's going to be. I think I just need maybe one more point over at 8, and that'll give me a good graph. Because I'm only going to do one more point, I'm not even going to use the table. I'm just going to plug 8 in and do it by hand. What's 3 times 8? 24 plus 5? 29. So it's log 29 over log 2. Log 29 divided by log 2. So I get 8, about 4.9. So let's go 8, 1, 2, 3, 4.9. And there's no reason why I picked 8. I just wanted one far enough away to get the curve. All right, and make your sketch. Any question on the sketch there? So that's how you sketch a log. Right. Intercepts are relatively easy to find, especially once you change it from log to exponential form. You get a pretty straightforward algebra 1 usually kind of equation to solve. All right, so that is sketching. And the last one. So the last problem is a problem involving what's called the Richter scale. So the Richter scale measures the intensity of an earthquake, and the scale is logarithmic. So when you have an earthquake, there's different intensities. Because it's logarithmic, does anybody know what that means if you compare a magnitude 4 earthquake to a magnitude 3? Yes, it's only one more on the Richter scale. But does anybody know what that means in terms of, like, say the amount of energy in the earthquake, how much more it is?
Probably 10 times more.
Yeah, it is. It's a factor of 10. So every time you go up 1 on the Richter scale, it's a factor of 10, and that's what we're gonna show right now. That'll be our last question. So if you compare like a magnitude 5 to a magnitude 3, the magnitude 5 is 100 times more energy than a magnitude 3. Right. Yeah.
Is the symbol before the capital B a T or a plus sign?
Plus b.
Okay.
So that's log of a divided by t plus b. Okay. So what do all the letters stand for? R is the magnitude. So when you read something or you watch TV and they talk about the intensity of the earthquake, R is the number that you hear. It's the magnitude. A is what they call the amplitude of the vertical ground motion, measured in micrometers. So that's something that they can measure with equipment. T is the period of the wave. And if you're thinking, like, what do you mean by wave? Well, imagine like you drop a rock in a pond, right? You get those waves that kind of come out from the center, and you can see them because it's in water. Well, the same thing happens with an earthquake. That's why the ground moves, right? There's a wave that starts at a center, and that wave moves out. You don't always see the wave because it's not like as much as water. Like in the ocean, you can get waves that are like several feet high. Usually in an earthquake, the wave going through the ground might not be feet high. Right? The wave is measured in micrometers. Right? But there is a wave that comes out from the center of the earthquake. And then B is a factor that accounts for the weakening of the wave. So if you take like a large rock and you drop it in a pile of sand, you'll see a wave. You get kind of a crater, but it will make a wave if you could watch it in slow motion. But it dissipates very quickly because the sand is, I don't know if it's because the sand is loosely packed and it just kind of absorbs the energy, versus water molecules are more tightly packed, so it kind of transfers the energy through the water. So we're going to figure out what we just said. What happens when you go up 1 on the Richter scale? What does that really mean? And we're going to look at this equation, see if we can figure that out. So here's our problem. So we're going to measure the intensity of an earthquake at 2 different times while it's happening. The early stage, we'll say that's like the start value of the earthquake. And then the later stage will be like the end value. So we have like an initial value and a final value. At the early stage of the earthquake, the amplitude of the vertical ground motion was A. At a later stage, it was 10 times as much. What does that mean as a number? We don't know. It just, whatever it started at, later on it was 10 times as much. What was the change in intensity? Okay, so we're trying to find the change in the magnitude. The magnitude is the intensity of the earthquake. How powerful is it? Okay, so first, let's just think about how do you find change? If you have a starting value and you have an ending value, and you want to know the change, what do you do with the two?
New value minus old value.
Yeah, you subtract them. Okay? And we're going to try to find a change that's positive. So which intensity do you think I would put first?
10.
The new intensity
New.
or the old one?
New intensity.
Yeah, let's put the new one first, just because we know the new one is bigger. So if we do a bigger minus a smaller, we'll get a positive number. If we did it the other way around, we'd get the same answer. It would just be the negative instead of positive. Okay, so what we want to do is find the magnitude, we'll call it later, because that's more powerful, minus the magnitude, we'll call it early. I'm just using the words from the problem. So we're going to take the magnitude later minus the magnitude earlier. So let's fill in everything we can into our formula and go from there. So let's start with the magnitude later. Okay. We got log of. Now, the only thing that's changing in this problem between the magnitude now and the magnitude later is the intensity. Okay. The period of the wave isn't changing, and the factor that accounts for the wave weakening as it spreads out through the ground, that's not changing. So they're both going to have a T and a B, and they're going to stay exact. They're going to be the same letter in both. So let's put divided by T plus B minus log T plus B. All right. Now, what we do have is a value for the intensity. What was the, amplitude? What was the amplitude later in the earthquake? Yeah, Holly? 10A. 10A. And what was the amplitude early in the earthquake? Yeah, just A. So now we want to simplify that as much as we can. So we have this minus that. All right. What's the first thing I could do here? And it kind of focuses on what's in front of that second set of brackets. What can I do with that symbol that's in front? Yeah. Yeah, distribute out your negative. So you're going to have 4 terms when you're done here. Log 10a over t plus b minus log a over t minus b. Okay. So I distribute out my negative. And what happens there now? Yep.
B's cancel out each other.
Right, the b's cancel out. And they should cancel out because anything that's the same at the early stage and the later stage shouldn't play any part in this equation. And there's other things that were the same too. So we should see those canceling out shortly. Okay, so now we have log 10a over t minus log a over t. All right. Now, we're going to use a property we talked about last week. How can I rewrite the log of a quotient? Yeah.
That would be log 10 plus log a over, or a minus log t.
So let's just we'll break up the quotient for now. So log, what did you say again?
10
10,
plus log.
still something next to it.
Oh.
A. Mhm.
Minus log t.
Perfect. So log 10a minus log t minus, and whatever you do to that second log, remember, you're going to subtract however you rewrite it. So if you're going to be breaking this log up, you need brackets because you're going to have a minus in front of all of it. Can anyone tell me how the second one breaks up? Dan, can you tell me how it would break up?
Just break up into log A minus log 10.
Log A minus log T. All right. Now, what can I do there? And I did a step very similar to this when we started. Yeah.
Log 10 plus
So this step is going to be very similar to one I've already done before. Yep.
Distribute the negative again?
Distribute the negative again. So log 10a minus log t minus log a plus log t. Okay. And now what's going to happen there? Yeah.
Both log t's will cancel out.
Right. Minus log t plus log t. That's another factor that was the same early on and later, so it shouldn't have anything to do with this answer. And it cancels out. All right. So now we have log 10a minus log a. All right. What could I do with that? Yeah. Well, they're not like terms because one's a 10a and one's an a. Like if it was log a minus log a, then you could just say it was like 0 or something. But they're not like terms. But there is another way we can combine them back together. Yep.
Can you rewrite it as log of 10a over a?
Yep. So log 10a divided by a. We're recombining it back together. And now what happens there? Yep.
These cancel out, so just log base 10 of 10.
So the logs cancel out. And now the a's cancel out. And now we're left with the log of 10. Base 10. What's log base 10 of 10? So what that means is if you have an earthquake and the intensity increases, or the amplitude of the ground motion increases by a factor of 10, that will be a change of 1 on the Richter scale. So every time you go up 1, it gets 10 times more powerful in terms of the vertical ground motion. Any question on that? All right, so that pretty much wraps up logs. So looking at change of base formula, graphing, transformations, and then an application to like a Richter scale kind of problem. There's another scale that people are usually pretty familiar with, and that's pH. That's also a logarithmic scale, like logarithms. Okay, so that's the homework. Make sure you look at this one, not the one in YouTube, because, or, I'm sorry, the one on Schoology. The one on Schoology has 2 lessons. We just did 1. Okay, so it's page 301, 8 through 11, 16, 23, 28, 32, 42, and 52. All right, so you've got just under 20 minutes left. You can use the time to try to get some of that done. If you have any questions, you can check in with me and I can help you out.